All right, welcome to section 5.5. We've been solving polynomials, right? Like x fifth, x to the fourth, x cubed, that type of stuff. Actually, I don't know if you've done the x to the fifth at this point, but we will eventually. And in this section, 5.5, we actually did 5.6 first. But 5.5 is to make a little bit more sense of like the solutions. So there's two goals. One is to understand that sometimes the solutions come in pairs. So what I mean by that is like we get like plus or minus 4i or plus or minus root 5 or something. So like we want to understand when we get pairs and like why we get them. And then also determine like we'll learn what a rational root is and we'll determine um, what ones are possible. And if you forget the word rational, just think of a ratio, right? A over b, like a fraction, that's a rational number. So we want to know when do we get these fraction, not when do we get them, which ones are possible, which fractional answers are even possible for a given polynomial. Okay, so if you want to copy down this chart, when you solve a polynomial, again like an x to the fourth or something like that, there your solutions they can either be real or imaginary, right? Imaginary with the I, and then inside of real there are two different types: rational ones, which again you might want to copy down. All rational really means is a over b. So something like 3 is considered rational because that's 3 over 1, negative 5 over 1. And also things like 0.25, that's considered rational because that's really just 1 over 4. So those are the rational answers. Um, and then you also want to put a note here that they don't necessarily have a plus minus pair. Let's see if I can actually spell this word. Have a plus minus pair. Okay, that word is don't there. Sorry, I didn't show it very good, but don't necessarily have a plus minus pair, right? And so the irrational ones, those numbers are like these square roots. So the most famous irrational number is pi, but for our questions, they're going to have these square roots in them. And so if they have a square root that doesn't come out perfectly, 5, 7, 3, then it's irrational. Something like root 4 is actually over in the rational world because that's really just 2. So the irrational ones are the ones that aren't perfect squares, right? And these will, if you want to make a note of this, always be in plus minus pairs. Again, sorry for the poor handwriting. I should have just typed it out maybe. Okay, and same thing with imaginary. Right? Imaginary are the ones that are I. You can see all the ones here have plus minus on them, and that's because these will always, again, be plus minus pairs. Be in plus minus pairs. Okay, and when you think about this, it makes sense, right? So if we think of like solving with like algebra steps, if I have like x squared equals negative 4, I take the square root, right? I don't get just 2i, right? I get plus or minus because of the square root, right? Similarly, if you look at our quadratic formula, when we're doing that, we oftentimes have this plus minus pair right there, right? So we get answers that kind of look like these plus minus pairs in the irrational and imaginary world. Okay, so again, the big picture of this slide is rational ones don't necessarily have a pair. They could. Sometimes they come in pairs. Right? In fact, I could think of one really easily. X squared equals 9. That would have an answer of both plus and minus 3. But there's no guarantee that these are pairs in pairs. The other two there are irrational, imaginary always come in pairs. All right, so I don't think you really need to write this down. I guess you could say they're conjugate pairs. Maybe if you want to write, I guess these two red lines might be helpful. But basically, if you have a plus b imaginary, then you have a minus b is also a root. And same thing with the square roots. If a plus square root of b is an answer, then a minus root b also must be an answer. So how this will look on the test and the homework is they'll give you and say, okay, we have a polynomial. We don't know how many roots or solutions. I guess roots and solutions mean the same thing. We don't know how many it has, right? We don't know if it's x to the fourth or x cubed or whatever. We don't know what it is. But we do know that these two are answers. Like in part A, these two are answers. So we have to say, are there any additional answers, right? Or roots. Roots again means the same thing as answers, right? And so the idea is this 3 is a rational answer. So going back to our chart, 3 is a rational answer. And so it doesn't necessarily have a pair, right? Versus the second one is an imaginary solution, and it does always have a pair. So if I'm finding additional ones, if 5 plus 2i is 1, then it's minus pair, right? We have the plus 1, so then the minus pair must also be an answer. Okay, so in B, I've got 2 answers so far. And if I look back, the first one is the irrational type. So it has a plus minus pair. So the pair would be 7 then minus root 5, because we already have the positive root 5 one. And you keep the 7, you don't flip that part, just flip the sign in between them, because then it would be 7 plus or minus root 5, essentially. And 8 is a rational one, so it doesn't guarantee to have a pair, right? So just the one extra answer there. All right, try C and D. If you haven't already given them a shot, try them. Pause the video. First two are rational, so they don't have pairs, 0 and 3. And then imaginary do, so we've got positive 8i. Sorry, we've got negative 8i. So there would be, its plus minus pair would be positive 8i. Okay, similarly, on D, all right, we have this one is an imaginary answer, and this one is irrational answer, right? It's a square root type, so they both have pairs, so just flip the symbol in between them. So if we have 4 plus I, then 4 minus I must also be an answer, and if we have 3 minus root 10, then 3 plus root 10 must also be an answer. Okay, so the second objective is if it's a rational, so we had the 3 types of rational, irrational, and imaginary. So if it is a rational one, that just means ratio, A over B. And so we know there's this thing called the rational root theorem, which I would definitely write down, which says that if it's a rational root, then it has to be in this form. That A part, the top part, has to be a factor of the constant, and the B part has to be a factor of the leading coefficient. All right, so these questions always trip students up because they say, what the heck, Mr. Westphal, why do we got to make a list of what's possible? And I'll try and explain that here in a second. But for now, we just want to say what is possible. So we're going to use this thing. We're going to say, we're going to take the constant term, which is technically negative 6. But in a second, I'll explain why it doesn't matter. I'm just going to have 6. Okay, and then the leading coefficient is the number out front, which is 2. Right, so now I need the factors of the constant. So 1 times 6 and 2 times 3. So those are our factors. For the constant, sorry, leading coefficient of 2, it has just 2 factors, 1 and 2. Okay, and so to make everything that's possible, these are all my possible numerators, and these are all my possible denominators. Right, so what I want to do is pair them all up. So I want to pair this denominator of 1 with all its possible numerators. Right, so if I do that, I would have 1 over 1, 6 over 1, 2 over 1, and 3 over 1. Right, and now I take my second possible denominator of 2 and pair it with all the numerators. So that would give me 1 over 2, 6 over 2, 2 over 2, and 3 over 2. All right, and so now you can usually like cancel out duplicates. So 6 over 2 is really 3, so I don't need to list that one again. 2 over 2 is really 1, I don't need to list that one again. All right, so those would be my possibilities, those 6 things. And then also, all right, the negative of all those. So what I usually do at this point is say, well, besides 1 being answer and 6 and 2 and 3, then negative 1, negative 6, negative 2, negative 3. So I just write a big plus minus to say that both positive and negative, all of these values. right? And these aren't the answers, right? This thing only has 3 answers. So we've got a big list here that actually has 12 different answers. And so these aren't our answers. These are just what is possible. Okay, and so if we want to find the answers, right, we can use the process from yesterday in 5-6, where we graph it, then use synthetic division, and then solve what remains. Okay, so what bothers kids on this is they say, if I want to find the answers, Mr. Westphal, I'm just going to graph it, and then I'll be able to see all my rational answers on my calculator. Okay, and that is absolutely true. All right, but the trick is your calculator, the window is between -10 and 10. That's the standard window. So if you don't know about this rational root theorem, there might be answers way out at 30 or 40, and you might have to like expand your window to look out there. All right. So what this really tells us is where do we got to look on our calculator for answers. All right. And so on this particular one, the regular -10 by 10 window would work just fine because the highest and lowest we get is positive and -6. Right. So we know that any rational answer would have to show up between -6 and 6. So in fact, the -10 to 10 window would work pretty good for this particular polynomial when we graph. Right, but that's really the point, is it tells you where to look. So that's why I do these sections in reverse order, is the whole point of the rational root theorem is to tell you where to look on the calculator. Right, and every year this is a little confusing to students, so the next day we actually review 5-5 and 5-6 and kind of tie it all together, and usually that helps a bunch. All right, let's try at least one more example to make sure we're okay. Oh, I should actually, sorry, before we go on, the book, this homework will actually have you find the actual rational roots. So that's when you use your calculator. So I'll explain what I mean here. All right, so I did the graph, and then if I want to find the actual rational roots, I can see them on my graph, right? So we have one at +2, which is definitely on our list. One at -1, which is again on our list. And then this one, right? We could find it, but based on our list, if it's a rational one, it should be this -1/2, likely, right? So we can see our 3 rational answers right there. So here is what was possible, and then here are our actual 3 answers to this polynomial, right? So let's try one more here where you list them, and then again, to find any actual rational roots, we can use that graph down there. So when it says find the actual ones, then we'll just graph them. But let's start with listing them. So pause the video, see if you can figure it out. Okay, so our constant is technically -44, but because we do the plus minus at the end, we can really just list it as 44. The leading coefficient is 2. So now I got to make a big list of my factors of 44 are 1 times 44, 2 times 22, 3 doesn't work, 4 works, 4 and 11, 5, 6. I think that's it. I think those are all our factors of 44. For 2, it's just 1 and 2. Okay, and now we got to pair them all up. So I'm going to take this 1 denominator and pair it with all my possible numerators. So I'm not going to draw it out because it gets kind of messy, but I'd have the denominator 1 6 times with all 6 numerators. So it'd be 1, 44, 2, 22, 4, and 11. And then we have the denominator 2. I'm going to list it 6 times. Pair it with all the possible numerators. Right? So I'd have 1, 44, 2, 22, 4, and 11. And again, cross off duplicates. So this one is really 2. This one's really 11. This is 1. I already got that one. I already got 22. So only real 2 new ones down there. Okay, and then don't forget, whoa, that's bad news. I might not even write that because I can't fit it in there. But it's just plus or minus all of those. So put a big parenthesis and plus or minus all of those. Okay, and then to find which ones are actually possible, look on our graph, and it looks like there's only one right out here at 11. Okay, and again, that's the whole point of the rational root theorem, right? Is like this one actually had answers, could have been way out to 44, right? So if I was using my calculator or whatever, I'd need to go all the way out to plus or minus 44 to see if there's actual answers out there, right? And this one had just one at 11. Final thing I want to say real quick is sometimes you won't have rational answers. So this one actually, these